So then we said, let's, as an example, make this point infinitesimally small and do some calculations there for the average rate of change. Okay. So rate of change of y over change of x, slope is the tangential point. All right. I want to be clear about functions. All right. Functions. So you've heard me throw that term around, but what is a function? Well, let me answer it for you. Function is, all right, if we're going to say a function of x equals something we're going to do with x, like x to the third plus 700 plus, exclamation point, squared, yada, yada. Right? We're going to put x, we're going to do all this stuff to it, and it's going to spit out a value. And we usually have been calling that y, but we could also call it function of x. So if I were to put in x, you would do all these calculations, which would tell you, all right, it's going to spit out this number here. Put in this x, it would spit out this number here. This number, it would spit out this x here. So this is a function. What we mean when we say a function is we put x in and it spits out some number based on the calculations that we prescribe. And in calculus, we learn that we can take the derivative of a function and it will give us the rate of change of that function at any point. And we can call the derivative a number of things. We might call it the prime, y prime, or the derivative, the first derivative of x equals rate of change of f of x. So we'll take a derivative, which is essentially finding the rate of change of the initial function. So we've got some function here that relates time to distance. It'll be f of x equals some junk. We could also find a function where we put in x, say 2 seconds, and it will spit out the speed, the rate of change at that time, say 2 seconds. Does that make sense? Okay, well, let's look at a specific example. All right. Okay. Let's do this, yes. All right, so I'm going to erase this. You have the intuition here, right, Nikita? Rate of change is speed. So suppose I were to tell you, let me do it like this. Suppose I were to tell you this is 1, this is 2. All right, at point 1, our distance is here. All right, say this distance is like 5. All right, at point 2, our distance is here, right? Let's say that's like 13. Okay, so from point 1 to point 2, we go from 5 to 13. So if I were to input 1 into this function, I were to put 1 right here, what would it spit out? Five, right? It would spit out 5. This line, this line tells us the function. So the function of x is the distance. So we put in time, it spits out distance. So if I were to put 1 into that function, which would be this line, let's just assume those numbers represent the mathematical equation of this line. I put in 1, it spits out 5. I put in 2 to this function, what does it spit out? 13. Fantastic. Now, if I were to take the first derivative of this function, and I could get the rate of change at any point. All right, now I'm going to put in 1. What is it going to spit out? No, it's going to spit out the speed at 0.1, at 1 second. And the speed at 1 second could be represented with a tangential point at x equals 1 and y equals 5. 5. Does that, see that upward sloping slope? So what does that mean? That means slow, fast, stop, backwards? Fast, yes. All right, if I were to put in 2 into this first derivative function, what would it spit out? 13? Okay, if I were to put 2 into this function, what would it spit out? Yes. But I don't want to, all right, so I know I put 2 in here, it spits out 13. I want to know if I put in 2 here, what does it spit out? The rate of change at 2 seconds. The speed at 2 seconds. You want to take a guess at what that speed is going to be? Right about here? What is it? This point right here, like what is it? Is it -1? Is it 0? Is it 1? Is it 50? I'll give you, yeah, those 4. Choose between those 4. -1, 0, 1, or 50.
0.
It's 0. Tell us why it's 0, Sanjay.
Because the slope is straight.
Yep, because the tangential point right there is flat. It's 0. Okay, so if I put in 2 to the original function, what does it spit out?
13.
Excellent. I put in 2 to the first derivative function, what does it spit out? Yes. Yes. Okay, fantastic. I'm going to erase this. I'll keep that up for a minute. We're going to look at an actual example that we did last time. And it's still time over distance, so I don't know why I erased that whole thing, but too much coffee. Alright, so distance on the y-axis. On the x-axis we have time. Alright, now the function we practiced graphing last time is f of x equals the square root of x. So, we put in x to this function, and what does the function spit out? Square root of x. Fantastic. Let's look at some examples. Let me erase this. Rate of change. So, let's see. Let's do f of 0, f of 1, f of 4, f of 9. Alright, so f of 0, f of 1, f of 4, f of 9. Okay. So I put 0 into this function. What does it spit out? 0. The square root of 0 is 0. Fantastic. I put 1 into the function. What does it spit out? 1. Fantastic. I put 4 into this function. What does it spit out? Close. I put 4 in here.
2.
Yes. Yes. 2. Now I put 9 in. What does it spit out? 3. Fantastic. And also, incidentally, you can't take the square root of a negative number. So -1, it just doesn't exist. So we don't have to worry about anything on the negative side. And you can see what's happening as x goes further and further along, from 1 to 0 to 1. Okay. So let's do 2. So 0, 1, 2, 3, 4, 5, 6, 8, 9, 10, 8. Okay, so we've got some points here. 1, 2, 3. Now we've got some points for our equation. We've got 0, 0. We've got 1, 1. We've also got 2. We've got 4 and 2. All right, and we've got 9 and 3. All right. So let's take a look at what might be happening with this function. So it might look something like this. Okay? So let's call this time over distance. So tell me the story. What's happening as this thing, this rocket, this car takes off and goes through time? Okay, so it's from 0 to okay, so we put in 0, we got 0. So we started time 0, 0 distance. The rocket's like on the ground. All right, then we put in 1, and it goes, say, 1 kilometer. So over the 1 second, it goes 1 kilometer. All right, and then over the next 3 seconds, how much further does it go?
2.
It goes 2 total, but it goes from, it was already at 1 at 0.3, and now it got to 2 kilometers. It took 3 more seconds. It took, so from here to here, 1 kilometer, from 1 to 3 more seconds, it took to go a whole nother kilometer. So the first kilometer it did in 1 second. The second kilometer it did in 3 seconds. So what's happening to the speed? Slowing down. Okay, and how would that look if we were to draw little tangential points at point 1 and point 4, just like we did in the past example? Well, it would start off, let me draw this again. Draw this with more of a curve. So it'd start off with a really, really high slope. And it would be the tangential point, like at 1/4 of a second, would be like super steep. Okay, and then when it starts to get up here, it starts to get less steep. And then gets up here, starts to get less steep. So you can see the slope starts out really steep, which is fast, high rate of change in y for every unit change in x, and then it starts to slow down. Okay, so let's think about how we would find the derivative of this function. We might do this. Alright. If we want to look at the rate of change at 1, let's do the rate of change from 1 to 4, 1 to 3. Okay. So, if we want to find a rate of change at 1, right, at point 1, what is the speed at that exact moment? Well, we don't have any tools yet to think of the speed at that exact point. But what we could do is we could say, well, what's the rate of change from 1 to 4? All right, so from 1 second to 4 seconds, how fast is it going? Well, it went, it went 1 kilometer over how many seconds? Fantastic. So, all right, so from 1 to 3, so let's see, rate of change change at x equals 1. So the change in y was 1, right? So in 1 kilometer. And the change in x was 3. So 1/3 kilometer per second. So we're going to call this time in seconds and distance in kilometers. Now, all right, so we don't want the change though from 1 to 4. We want it right at 1. So then let's make that smaller, right? Let's go from, say, 1 to 3. Let's do that. All right, so the rate of change from 1 to 3. And let me break this down. Let's go back from 1 to 4 to a second. How we did this is we said from the change in y, it got from all the way to 2 and it started at 1. So we said from 2 minus 1, all right, divided by 4 minus 1. 4 minus 1 equals 1 minus over 3. You see how I did this? So it got to, at 4 seconds, it was at 2 kilometers, and it started at 1 kilometer in 1 second. All right, and then it's 2 kilometers over 4 seconds, and 1 kilometer and 1 second is where it started. So that's how we got the 1/3. So let's say at point 3, let's go the rate of change from 1 to 3. Okay, so what is the y value at time equals 3? If we were to put 3 into this function, what would it spit out? Put 1.7. Okay, 1.73. All right, and 1, so at 3, all right, it would be 1.73 minus, what was the distance at 1? T equals 1? It was 1, right? Minus 1, and over 3 minus 1. All right, so what do we get when we do that? So it's 0.36. Okay, so this is 1/3, which equals 0.33, and this is 0.36. So which one of these is a faster slope, is a faster speed? 0.36 is a bigger number, so it's a little bit of a steeper. So from 1 to 3, it had a higher rate of change. So and we'd expect that, because as we're trying to get closer and closer to 1, we would expect that slope to curve up. So what we decided to do, or what the textbook showed us to do, is let's pick a point and make it as small as possible. And let's call that point H. All right, this little point here, H. All right, and let's see what the rate of change is in H. So we make that as small as possible, and we assume that that gets even smaller. So, which gives us the formula for the derivative, which, all right, the derivative, so if f of x equals some function, f prime of x, f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. So in this example, we said, all right, f of x plus, this was the example, the rate of change from 2 to 4, right, or 1 to 4. All right, so this is the larger number, x plus h. Well, we said that is 2 kilometers. All right, the smaller number is 1 kilometer, f of x. All right, and the distance that traveled was 3. Let me say that again because it's confusing. All right, this is, we put 4 seconds, the larger number, into the function, and it spit out 2 kilometers. That's the larger distance. All right, we put 1 second into the function, it spit out 1 kilometer. So it covered a distance of 1 kilometer, and how long the value of x was 3. So let's find out what happens when we make this as small as possible. We imagine that x goes to 0. Make sense? Makes sense, Brendan? Brandon,
Yeah.
this is feeling like this is candy.
Yeah,
This is just like
from last week.
you're just rocking and rolling. You're falling asleep?
Hmm?
Is that what you're doing? All right. So let's do that with this example. So let's say, all right, f of x equals the square root of x. F of x equals the square root of x, and we have all these values for 0, 1, 4, 9. So I want the derivative function, where I can put in 0 seconds, 1 second, 4 seconds, 9 seconds, and this function will tell me the rate of change or the speed at that point. So that's going to be f prime of x equals the limit as h goes to 0 of the square root of x plus h minus the square root of x all over h. Is that right, Brandon?
Yep.
Okay. So that's it. All we need to do is solve and get that into a form that is usable. Now here's the thing. Right now, we've got an h in the denominator. And if we're going to imagine what happens when h goes to 0, that presents a problem, because you cannot divide by 0. So if I have one piece of pie and I divide by 0 people, it doesn't make sense. It's not 0, it's just a number that doesn't make sense. So I need to find a way to get that not in the denominator. It's okay if it's in the numerator, because I can imagine h goes to 0, then I've got something I can work with. So, where am I going to do this? I'm running out of real estate here. All right, let's do it like this. Okay, let's keep track of our functions. So we've got f of 0 equals 0. We've got f of 1 equals 1. We've got f of 4 equals 2. We've got f of 9 equals 3. But we want to know some information about the rate of change. I want to know the rate of change at 0. F of 0 equals what? All right. I also want to know the first derivative of f of 1 equals what? So when I say I want the derivative of f at point 1, what question am I asking? Yes, I want the speed at the time x equals 1. I also want to know the speed, first derivative of f of x at f of 4 equals an f prime of 9. All right, I want that information, and I don't have it yet. But what I do have is a formula for calculating that. All right. And that's going to be f prime of x equals the limit as h goes to 0 of square root of x plus h minus the square root of x all over h. All over h. Okay. And what's the problem with that as it is right now? Why can we not say we're done? Well, this is the prime. This is the formula for the prime. But why is it not yet in a usable form? Brandon?
No, you have h's in there, but you can cancel off.
Well, right now we have h in the...
I mean, also you can't divide by 0.
We cannot divide by 0.
Jumping at.
Yes. Okay, so we have h's we want to cancel out. Now, these square root signs, that's something that we want to think about getting rid of as well. We want to see if we can get rid of these, what are called radicals. Square root signs are called radicals. And we can rationalize, do what's called rationalizing the numerator by getting rid of these radicals. So when you see square root signs, you want to think about how can I get rid of those square root signs? Because once I get rid of those square root signs, we can do as Brandon says, maybe cancel out some of the x's, simplify this, get something besides h in the denominator. And the way we can do that is we can think about factoring this. We can imagine this as some quantity minus another quantity, and we can multiply it by something to put little square root signs, to put little squared signs on each of those. So take a look at your factor sheet and look at the point where it says where it says a squared minus b squared. I don't have mine. I gave mine away. Oh, I have the original. Yeah. A squared is the top one. A squared minus b squared. All right, so let's think about how we can use that. It says, let's see, a squared minus b squared equals what? A minus b times a plus b, or is it the other way around? It's the other way around, but it doesn't really matter. Okay. So let's look at this as a minus b, and let's multiply it by a plus b. And then once we do that, we can put it into this form. Right? So let's multiply this by a plus b. This is a, this is b, so this is a minus b. So let's multiply that by the square root of x plus h plus the square root of x. Right? So that takes care of the top. All right, we're going to multiply. And then we're going to be able to put it in a squared minus b squared on the top, right? We'll get rid of these radicals. Now, but what do we have to do with the bottom, though, to make this legit? Do we have to put anything there?
Yeah.
Yes. What do we have to put there?
The same thing.
We have to put the same thing. We can multiply by anything by 1. All right, and if we have the same thing in the numerator and the same thing in the denominator, that's the same as multiplying by 1. So we can multiply both the top and the bottom by square root of x plus h plus the square root of x. You see how that's 1? This square root of x plus h plus the square root of x over the square root of x plus h plus the square root of x. This is the same as this, so that's like multiplying this equation by 1. Right, Sanjay? So we're good. We can multiply this by 1. And if we can do it in a way that helps us get rid of these radicals, these square root signs, then we're golden. Because what we've done is a minus b times a plus b. We now know we can make it a squared minus b squared. So, and this then becomes, on the top, x plus h squared minus the square root of x squared. That when we combine this and this, that's what we get because of the first thing on our factoring sheet. Question now is, what do we get in the bottom? What do we get in the denominator? Well, we just multiply this out. All right, we have h times this plus h times this. So we have h times the square root of x plus h plus h times the square root of x. Okay. So what we can do? What can we do with this top set? We've got the square root squared. Remember the whole point of doing this was to get rid of the square root signs? So let's square root those. So this just becomes x plus h And this minus becomes x. All right? So this is looking pretty good, right? We've got a plus x, a minus x. This is looking like it's going to be something that's going to simplify our life and get h by itself and make this a simple equation for us. Now on the bottom, what do we have going on down there? On the bottom we have, let me pull this h back out. Let me say we've got an h here. All right, it's h times the square root of x plus h plus the square root of x. So we've got an h by itself on the outside. That may be something that we can cancel. And we can. So we've got the x plus and the x minus. These two cancel each other out. And now we have h on top, h on bottom. As long as we have this h on the outside of the brackets multiplied by something, we can cancel those. Right? Now, we're rocking and rolling. We have 1 over the square root of x plus h plus the square root of x. And remember, the whole thing we're doing here is the limit as h goes to 0. So now we can think about this h going to 0 without getting a 0 in the denominator, because this h is part of something else. So we just put in 0 for this h. And as long as it doesn't give us an undefined term, which would be 0 by itself in the denominator, then we're good. So this equals 1 over the square root of x 1 over the square root of x plus the square root of x, which equals 1 over 2 times the square root of x. F prime of x equals 1 over 2 times the square root of x. So this is a function which gives us the rate of change at any point along x. So, my question to you now, tell me how fast this rocket is going at time equals 4 seconds. 2. How are we going to do this? How are we going to approach this? Nikita, why don't you just tell me, I want to know how fast this is going at time equals 4 seconds. And remember the whole product of this. F prime x equals 1 over 2 times the square root of x. All right, that is the product of all our work. We now have a derivative function which will tell us the rate of change or the speed given any x. So my question to you, how fast is this rocket going at time equals 4 seconds? Sanjay, how are we going to do this?
1 divided by 2 times 2. 2 times the square root.
Outstanding. We just put in 4 here. We get 1/4, right? Square root of 2 is 2. So f prime of 4 equals 4. Okay, let's do the others. All right, how fast is this rocket going at time equals 0? 0. We put 0 in there and we get 0. How fast is this rocket going at 1 second? I miswrote this. I said 4. It's not 4. It's 1/4. 1/4. All right, at time equals 1. Yeah. All right, put 1 in here. That's 1, so it's 1/2. All right, 1/2. How about 9 time equals 9? Yes. 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 Okay. So, and that makes sense, right? As time goes on, this rocket is getting slower and slower. And the tangential points are getting flatter and flatter. And they're going to get closer and closer to zero as this levels off and essentially doesn't go any distance until it goes 100,000 seconds. Then it goes a tiny bit of distance as this gets flatter and flatter. The rocket's going to get slower and slower. Okay. Okay, fantastic. All right, next thing, which we did a little bit of last time, we just barely touched on. Is everyone good on it? Nikita, you're good on this? Sanjay, you're good on this? Brandon, I know you're good on this. So the last thing we did in class last time is we said, let's find the equation of the line tangent to f of x equals the square root of x at x equals 1. So is it okay if I erase this? Yes? Okay. Actually, I shouldn't have erased that one thing. Let me just, what did I say? So, f, what do we decide? F? Got it. F prime of x equals 1 over 2 times the square root of x. All right, that was the fruit of our labor of that whole work. So, a question now, in the equation of the line, find the equation to the line tangent to f of x equals the square root of x at x equals 1. Alright, the equation to the line to f of x equals the square root of x at x equals 1. So, we are looking at f of x equals the square root of x. This is our equation we're working with. We want to know, at the point x equals 1, alright, what is the slope of the line tangent? So, we can just eyeball it, 1 here. And I'm going to draw a roughly tangent line. Alright, and I'm going to say it's this. Alright, that's the line I want. I want the equation of that line at x equals 1. First question. So everyone understands what we're asking, right? What we're trying to accomplish? The equation of this line. First question. What is the slope of this line? The green line, the one that I just drew that we're looking for. What's the slope, or how do we find it? Go ahead.
No, I'm trying to figure out. I forgot what it's called.
The derivative?
Yeah, there you go.
Yes.
The derivative.
Okay, tell me about the derivative. Keep
Yeah,
talking.
I find the derivative of 1.
Okay, we find the derivative function and we put in 1. And it spits out the slope at any point along this line. So Sanjay, can you summarize that for us? How do we find this slope of this line that is tangent to this function at point 1?
Find the derivative of 1 and it spits out the speed.
Yes, spits out the speed, which is also the slope. Does that make sense, Nikita? Okay, so Nikita, what is the slope of this line? You can just tell me the value. This green one, the one we're trying to find. Sanjay, remind Nikita how we're going to find the slope of that line.
Oh, we have to find the derivative for whatever the number it is.
Yes. Yes. Okay, so remember I drew this line. It's at time equals 1. It's tangential, right, to this equation at this point, and I drew it. Question to you is, what is the slope of this line? It's a number. It's a number. It's going to be like 0. It's going to be -1. It's going to be 1,000. It looks about like 1, but it's not quite 1. Okay, we can find out exactly how much by looking at one of these numbers. I'll give you a hint. It's either this one or this one. 1/2. Yes. Yes. So we found the derivative of this function, and we put in 1, and it tells us the slope at 0.1. Okay, so we know the slope equals 1/2. We also have points on this line. We know that x equals 1 because that's what we're given. The point is 1. Question is, what is y when x is 1? So if x is 1, all right, what does y, what is y in, what is y in actually either equation? Or no? What is the point? The point, yeah, we want the actual point on this line. So when x is 1, y is 1. And we know that by looking back to the original equation, because we're just looking at the point. Okay, so we have the slope and we have a point on the line. And if you look on your factor review sheet, you can see at the bottom something called point-slope form.
How do we get 1/2?
Okay, yeah, let's back up a minute, because this is important. So, Sanjay, can you explain that to us?
We have to find the derivative of x.
The derivative of the original function.
The original function, which was 1, so we're looking for 1. And we did that earlier, and we found out that it was
So we have to multiply 2 times whatever the value of 1.
We put it in here. So we put 1 in here. And we put 1, the square root of x is 1 times 2 is 2, 1/2. So we put 1 in, we get 1/2. All right. We put 9 in, we get 1/6. We put 4 in, we get 1/4. So to summarize that, Nikita, please tell me how fast this rocket ship is going at 9 seconds. Yeah, 1/6 kilometer per second. Please tell me how fast this rocket is going after 4 seconds. Yes. Yeah. After 4 seconds, how fast is this rocket going?
1/4.
1/4 kilometer per second. Yes. Okay. After 1 second, please tell me how fast this rocket is going.
1/2.
1/2 kilometers per second. Say kilometers per second. Yeah. All right. Next question. Please tell me how much distance this rocket has traveled after 9 seconds.
3 kilometers.
Yes. Please tell me how much distance this has traveled after 1 second. 1 kilometer. Please tell me how fast this rocket is going after 4 seconds.
1/4
Per second. Yes. Okay, so say kilometers per second, so you're clear on that. Yeah, you got it. So this is distance, the original function. This is speed, the derivative function. So we said at point 1, we want to find the slope of the line that is tangent to the original function at point 1. I drew it. We calculated the slope as 1/2. We also know that x is definitely one of those points. we need to know what is the y coordinate by going back to the original function. And when we put in 1, we get 1. So we have a point, and we have the slope, and the thing at the bottom of the review sheet tells us everything we need to do to write out the equation for this line. Point slope form, which is y minus y1, right, which y1 is the actual y. So we write y minus the actual y of 1 equals slope 1/2 times x minus x1, which is the actual value of x. And then that's it. We just solve. Does everyone understand how I got this point slope form finger? Suppose I were to tell you that this wasn't 0.11, this was 0.63. How would I write a line that had a slope of 1/2 and contained a 0.63? How would I write that in point slope form? Y minus 3, excellent, times equals 1/2 times x minus 6. Okay? Okay, it just gets a little confusing because they're both 1, and then it says y1, so 1, 1, 1, 1. All right, so y minus 1 equals 1/2 x, and 1/2 times -1 is minus 1/2, right? So let's add 1 to both sides, so we get the y by itself. Add 1. All right, so we get y by itself on this side equals 1/2 x stays the same. What's -1 plus 1? -1/2 plus 1, I'm sorry. -1/2 plus 1. Plus 1. -1/2 plus a 1. Yes. Positive 1/2. That's it. Y equals 1/2 x plus 1/2. Righto? Rocking and rolling? Do the calculus dance. It's just like there's so much algebra just for one answer. Like, yeah. Okay, so does that make sense, Nikita? All right, so let's take a look at some examples from the book. Page 7, correction, page 617, number 33. Brandon's just going to take us through this one, and then we're going to get some new material for him. 617, number 33. Okay. A tourist drops, is everyone there? Or is that good? Yeah, okay. All right. A tourist drops a stone off the cliffs of Moher, Ireland, and it falls into the Atlantic Ocean. Let S of t represent the position of the stone in feet above the sea level, t seconds after it was dropped. Explain what the equations S of 7 equals 7 and S prime of 7 equals -224 mean in practical terms. All right. You think about that while I erase the board. All right, so we want to know, all right, S of t, boom. Equals position of stone. Equals position of stone after it is dropped after t seconds. All right, so your question for you is S of 7 and S prime of 7. S of 7 equals 0. S prime of 7 equals negative 224. Okay. What's going on? Well, I'll tell you what's going on. We've got a tourist standing on the top of cliffs of Molière. Apparently it's a ways up. She or he drops a stone, and then that stone, as it's falling, is probably getting faster and faster. Yeah, it starts to slow, like gravity pulls on it, and it gets faster and faster. And we've got an equation which is getting faster and faster, but it's also getting closer and closer to the water. Obviously, I think I made this joke last time. The stone doesn't go up, it goes down.
Yeah.
Right, the stone gets closer and closer to the water. So as time goes on, the stone is getting closer and closer to the water. And at some point, it's going to hit the water, and it's going to have a certain speed. So we've got an equation that tells us the position of the stone, meaning how close it is to the water. This is just distance backwards. All right? It starts off a certain distance, and the distance gets less and less and less and less, and then it hits the water. And then we've got a derivative of that function. So let's start with the first one. So S of t, if I tell you t, what will this equation tell me? What will it spit back at me? I tell it, say, 4 seconds. What does it tell me?
Distance.
Distance from what?
Distance from the water.
Distance from water, exactly. So 4 seconds, 5 seconds. So what's happening is that as time goes on and on, is the distance getting bigger or smaller? Smaller. Okay, good. So I put in distance. The original function spits, I put in time, excuse me. The original function spits out distance from the water, and it's going to get smaller and smaller. Now what is the derivative of the original function going to tell me? Let me erase this for a minute. Forget about these numbers. Just think about what's the derivative of the function, S prime. This tells me distance from the water. What does the derivative tell me?
The speed at that distance.
Okay, same thing we're doing before. All right, so in practical terms, what meaneth S of 7 equals 0? Yeah, let's start with that. S of 7 equals 0. What does that mean? Time? Okay, I'm sorry, but I cannot accept time as an answer. Position of what?
Stone.
Position of the stone. Okay. Time, position of...
In seconds.
Okay. I like where you're going with this, but what I will tell you is you have enough information to be very specific about the time and the position of that stone. And I'm asking you for that specific information right now. Sanjay, help us out.
At 7 seconds, the stone is on the water, 0 distance from the water.
Yes.
Stone at the water.
7 seconds, the stone hits the water. What if I were to tell you S of 5 equals, 300? What would that mean in practical terms? S 5 equals 300.
That 5 seconds would be 300 feet from the water.
Yes. 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 Okay. How about this one? S of 7 equals negative 224. Remind us what the derivative, F prime, S prime, what does that tell me?
Okay. Speed. Yeah, got you right there.
Okay. God, man, my odyssey here with that. It would be speed, yes. All right. All right, so so speed. Let's try this. No one's really watching, right? What if I just like pour it on? Oh! Oh god! Oh god! Cold water I hear set. Oh boy. All right, one of those funny teaching moments I'll reflect back on and laugh. Okay. No, it's fine. It's fine. It's fine. I just hope no one comes in and wonders what the hell is going on here. Okay. So s prime of 7 equals negative 224. What does that mean in practical terms? You know? Yeah. Okay, the rate of speed at 7 seconds, it gives us that information, and what is it? Yeah, negative 224 means it's going down 224 feet per second, I think. Okay. Right? We're good? All right, let's move on to the next one. Number 36. A polling firm determines that the percent of likely voters who support a certain mayoral candidate can be represented by a function P of t, where t is measured in weeks since the candidate entered the race. Interpret the given equation, including units. P prime of 2 equals 0.5, and P prime of 6 equals 3. All right. I don't think this worked. Oh well. Sure, it is had a lengthy term of service. Okay, let me erase this. Get our palette ready. Okay. Polling firm decides that the percent of likely voters who support a certain mayor candidate can be represented by a function P of t, where t is measured in the weeks since the candidate entered the race. Because you've got this function P of t. You put in t, which is weeks since the candidate enters the race. What does it spit out? You input weeks, time, right, number of weeks, 1 week, 2 weeks, 3 weeks. And what does this function spit out? Yes. Input, time, spits out. Okay. So that's the original function. What if we were to take the derivative of that function? The derivative of any function tells us the rate of change of that function. So in practical terms, the derivative of this function tells us what? It tells us how many more voters, the rate of change.
Oh, so how many more voters came each month?
The rate of change at that exact point. All right, it's their change.
Week 1, week 2, something like that.
Yeah, week 1. All right, so maybe 40% of voters support this candidate, and it's changing at the rate of 2% per week. That's the derivative would tell us the 2% per week. The original function would tell us 40% of voters. Okay, so let's P prime of 2 equals 0.5. Please interpret that for me in practical terms. Yes, week 2.
The rate of change is 0.5%.
Yep, 0.5% per week. Fantastic. Does that make sense, Nikita? All right, Nikita, can you take B for us? P prime of 6 equals 3. Yes, every week 3% more voters. So maybe this candidate took a minute to get some name recognition, and now there's have all these commercials, whatever. So by week 6, they're gaining 3% of voters per week. Yes, got it. Let's look at 37. All right, you plan to take out a 30-year fixed rate mortgage for $300,000. Let
P of R be your monthly payment if the interest rate is R% per year, compounded monthly. Interpret the given equations, including units. Okay, so you've got this function, P of R, where the interest rate is R. So you input the interest rate, and it spits out what? You say the interest rate is 4%. And what does it spit out? Exactly.
5 years, the monthly payment will be like 1,600.
Close. Not 5 years at 5 what?
Fixed rate of
5%. Yeah. So you input the interest rate. You got it. Yeah, you got it. I can tell you got it. You have it. So you input 5% interest rate. You're paying $1,610 per month. Okay. How about P prime of 5? So the derivative of any function tells us the rate of change. At that particular point, the rate of change is 183. What does that mean in practical terms? Oh, it's by whatever units. So right now we're at interest rates, or interest units, so I guess it would be 1. So from 4 to 5 to 6 to 7%. Whatever the unit it gives us. We don't ask any questions beyond that. Okay. So what does that mean in practical terms? Anyone who wants it. Nikita got the first one. B is open for me. P prime of 5 equals 183.37. Get started on the next subject while I'm waiting. Oh, yeah, you're good. You're doing this blind. You all have it.
It gets it at the rate of 5% interest.
Okay, so 5% interest is the rate.
So interest will be increased.
Okay, so you input 5% interest into the original equation, and you get a payment of $1,600. P prime of 5 tells us the rate of change at 5%. So at 5%, for every 1 unit you increase the interest rate, you're going to increase your monthly payment by $183. Now, maybe one of those things is not a straight line. Like it may be like 6% is 187, 7% is 104 because you get a break once you're really high. I don't know how it works. Okay, yeah, because it's compounding, something like that, like less time. I don't know. I guess I can figure it out. But okay, good, fantastic. How are you all doing? Okay, can we keep going? Let's keep going. Let's fire through this stuff. All right. So fortunately for you all, we do not have to do that H thing for very much longer. We've got some very exciting things. First is the power rule. All right, if f of x equals x to the n, then f prime of x equals n times x to the n minus 1. Pretty good stuff. Let me show you what that means. Suppose I were to give you the function y. God, shoot something here. I'm going to find one marker that works. I'm not going to set it down the whole rest of the class. Sorry, you're going to get the same color. So if I were to give you y equals x to the 4th,
All right, instead of doing the h plus h minus, you're going to use the power rule, and you're going to tell me y prime. And is everyone okay? I'm using y prime, f of x prime is all the same stuff. Equals, we take the 4, put it in front of the x. So 4 times x to the x raised to the 4 minus 1 is 3. So y equals x, y prime equals 4x to the third. Rocking and roll. How about f of x equals 2 times x to the 5th. All right, I want to know f prime of x. 2 times what?
X raised to 4.
Close. Remember, we have to take the 5, bring it down here, multiply it by 2. And then we have 5 minus 1 is 4. Sanjay, you have an answer for us? F prime of x?
No.
Brandon?
10x to the 4th.
Yes. 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 Okay. So what we do is we take 5, bring it down here, so f prime of x equals 5 times 2 times x to the 5 minus 1. And as Brandon showed us, that is 10x to the 4th. Make sense? All right, let's try one more. F of x equals 3x to the 6th. Question for you. F prime of x equals what? We're going to have to wait. Don't say the answer. Don't say the answer yet. I want all 3 of you to get the correct answer. And then we are gold. Do you have it?
18 plus x to the 5.
That's it. I wrote it down. This one.
Didn't even have to write it down. Okay. Fantastic. All right, so that is the power rule. Valuable, cool stuff. All right, let's erase all this. All right, next is the constant rule. Constant rule. If f of x equals k, k meaning a constant, meaning some number, 5, 16, negative 463,000, then f prime of x equals 0. Ha. Ha ha. If any constant, the derivative of that number equals 0. Let's think about y for just 1 second. Suppose this is x, this is y. All right, suppose I have the equation y equals 3. How do I graph that equation? Go ahead and graph that equation on your paper for me. Y equals 3. Draw a line, y equals 3. Does everyone have it? Y equals 3. Nikita, you have it? It's a line. It's a whole line. Y equals 3. That's sort of a dash. It's a point. It's a point. It's not a line.
Oh, a line.
A line. What do you have?
It's still draw a longer line. I want a longer line. That may be right. Yeah. Draw arrows. Show me guys. They're not. Yeah. Yes, that's right. Yes. So what's this one here?
Yeah, that's fine.
Okay. All right. Yes. That's it.
Just going up.
No, it's y equals 3. No matter what x equals, y equals 3. I don't care what x equals, y equals 3. If x equals 0, y equals 3. X equals infinity, y equals 3. Okay, so this is the equation y equals 3. So now tell me the derivative. Y prime equals, what's the derivative of this line? What's the slope at any point on this line?
0.
0. The slope at any point on this line is 0. Hence, we have the constant rule. If f of x equals a constant number, f prime of x equals 0. So, a couple quick examples. Alright, y equals 5. Y prime equals what? Very good. If y equals 2x plus 5, now this plus sign, we can take the derivative of these separately. We can first take the derivative of this, and then take the derivative of this. And actually, this is a hard. This is going to be confusing, so let's make it not confusing. Y equals x to the third plus 5. Alright, I want you to tell me the derivative, first derivative of y. 0? This part is 0. What about this part?
Is it x plus 0?
Use the power rule for this one.
Oh.
Yeah, use the power rule for this one. Power rule for this one, constant rule for this one. 3x squared. That's it. Right? This goes away. Done. Okay. Fantastic. Let's take a look at page 622. Example 3. All right. Actually, don't look at it. Don't. Turn your heads. Let me write it down. All right. Y equals 8x to the 4th. All right. Y equals 8x to the 4th. Tell me what y prime equals. Eight x to the 4th is y prime. What?
32x raised to the cube.
32x to the cubed. Yeah, good. All right, now don't look at the answer. Negative 3/4 t to the 12th. Y equals negative 3/4 t raised to the 12th. All right. Y prime equals what? What?
175 g raised to the
What do you got, Brandon?
I got negative 9t to 11.
Negative 9 t to the 11th. All right, Sanjay, you're the tiebreaker. Whose do you like? Do you like this one, or do you like 0.75?
I don't know.
Well, Sanjay, how are you going to do it, right? You're going to take 12.
Times 0.75.
12, yeah, times 0.75 times negative 3/4. All right,
So it's 16.
not 16. 12 times negative 3 is 36 over 4, which equals negative 9. T, 12 minus 1 is 11. Okay. And if you have any questions, make a note on example 3. It's got it all spelled out for you. All right. Okay. So, 6x cubed plus 15x squared. All right. Y equals 6x cubed. That's it. Don't look at anything on the piece on the book. 6x cubed plus 15x squared. Plus 15x squared. Okay, and I mentioned earlier this plus, you can just do these separately. Use the power rule here, and if there was a constant, you could just use the constant rule. This addition, subtraction doesn't mean anything. Y prime equals what? Yeah, what's the answer, Sanjay?
30x.
Third?
15x.
What?
15x. And 30x.
18x plus. You have to keep the plus the same.
Oh, plus.
Yeah, but it just doesn't change the way you work the derivative. Plus what?
30x.
30x. Okay, close. What are you missing? There's one thing you're missing. Brandon.
Square.
3 minus 1 is 2.
Oh, yeah, okay. And then 30x. That's the one.
Yep, you got it. You got it. Okay. Ooh. Okay. Now we're going to start to get a little tricky. It's not that tricky, just a little tricky. All right. P of t equals 8 times t to the 4th minus 6 square root of t plus 5 over t. Oh god, I'm going to shoot myself. Oh god, this is so scary, isn't it? Oh boy. How are we going to do all this? Well, let's take a look at that factoring sheet. Exponent review sheet. We've got some good stuff down there under exponents. We have a, the negative n equals 1 over a to the n. We could write those either way, right? We also have a to the 1 over n equals a to the root of n. And lastly, we have a over m divided by a over n equals a to the m minus 10. Have you all seen these kind of before? Maybe? It's just a different way of writing them. So when we have something like the square root of t, well, we can write it in a way that makes it easier to use the power rule. Namely, we might write it like this. The square root of t, we would write it to the 1/2. T raised to the 1/2. And when we have t in the denominator, we might use this one. T raised to the negative 1. So, we could rewrite this. P of t equals 8 times t to the 4th minus t to the 1/2 plus 5 times t to the negative 1. And this is an example out of your book. So I can direct you to that example so you can look at. In fact, I'll do that right now. It's example 4 on page 623. So when you go home, you can forget exactly what we did. You can say, oh, that's what we did. Okay. So everyone's good to hear, right? You good here, Nikita? No? Okay, so how do we go from... all right. So...
Simplify like 8 raised to 3 4.
What's that?
Like the 8 thing first one. Do you
Oops.
you don't know how to use the power rule for 8 t raised to 4?
This is not the derivative yet. We're going to find p prime in a minute.
Oh,
P prime of t equals... All we did was simplify the exponents. Are you good now?
yes.
Now you're good. All right, good.
I was thinking.
I'm glad we straightened this out. So, well, let's do it then. Let's find the derivative. P prime of t. What is the function which tells us the rate of change at any point on that line? Let's crunch it out. Use some power rules. All right, does everyone have the answer? No? Okay. No, that's the answer.
T.
All right, I don't know. Well, let's work it out. Everybody ready to work it out together? Let's do it. So 4 times 8, what's 4 times 8? 32 t to the third, right? All right, and we've got -1 t times 1/2, right? So -1/2 t raised to the -1 minus 1/2 minus 1, right? What's 1/2 minus 1? -1/2 to the -1/2. All right, plus 5 plus excuse me. This -1 times 5, -5 times t to the what? Does that make sense, Sanjay? Okay, let's put these terms. Let's put this to the -1 and to the -2. Let's put that back into terms that we're more familiar with. So 1/2 t to the -1/2. Let's just say t to the -1/2 is, what is that? It's equals. Oh, this is a tough one. It's 1 over the square root of t. Is that right? That's right, right? Because it's negative, meaning we 1 over t, and 1/2 means the square root, the second root of t. Similarly, t at the end to the -2 equals 1 over t squared. Okay. Yes. Yeah, I think that's the little exponent stuff's going to sink in. Okay. Let's keep going. We've only got like maybe 15 more minutes. Maybe 20 more minutes. 20 minutes. 22, 23. 628, number 5. All right, 628, number 5. Go ahead and crank that out at your leisure there. 628, number 5. All right. Y'all working? You got it? You got it? Okay, sure. You got it? Yes. And you can just write, you don't have to say minus 0. Just doing that. So the answer is, are you ready for the answer, Sanjay?
Yes, sir.
Okay, it's number 5, it's 4x to the third plus 9x squared minus 8. Squared minus 8. Does everyone get that? Yes. Fantastic. Okay. So let's do number 15. 628, number 15. Alright, so let's take a look. 6x to the negative 5. 5 times negative 5 times 6 is negative 30x to the negative 6 minus, actually it's going to be a plus, because negative 1 times 2 plus 2x to the negative 2, right? Right? Oh, and also I forgot to mention, do you know what x equals 0? X raised to the 0 is equal to 1. Everyone knows that? You ever get in a situation like that? Okay. So, rocking and rolling. Okay, now let's do some. Oh, 33.
Minus plus 6.
What?
30 raised to x raised to plus 6.
So negative 5 minus 1. That's negative 5 minus 1 equals.
Negative 6.
Do you have a question about this?
Yeah, but doesn't minus 1 is equal to plus?
This is negative 6. I know exactly what you're thinking of. It's just, you have negative 5 and you take 1 away. But if you say negative 5 minus negative 6, what's that? What? Minus 1? Yes. Okay, good. All right, let's do number 33. And that dx, that's just another fancy way of saying the derivative. Actually, yeah, dx. This is derivative of x. You can say dy over dx, derivative of y with respect to x. So you can say the derivative of x. They're just showing you different ways here. Go ahead. Number, what are we, 33? Yeah, 33. Everyone ready? No, no one's ready. You got the answer, Brent?
Partially.
Okay, alright, let's do it. So 9x raised to the negative 1/2. What do we do with this? This figure here. How do we make that easier to use the power rule on it? So this is in the denominator, which means we can put it in the numerator with a negative sign on it. We can bring it up here, we just put a negative sign on it. So 2x to the negative 3/2. You can go numerator up, puts a negative sign, below the numerator, don't use a negative sign. Once we get to this point, we're golden, right? Negative 1/2 times 9 is negative 4.5x raised to the what? Negative 1 minus 1 is negative 1/2, which is negative 3/2. Negative 1/2 minus 1. Negative 1/2 minus 1 equals negative 1 1/2, or negative 3/2. Yeah, that's fine. That's cool. Sanji, does that make sense? Nikita? Okay. Fantastic. And then, so we've got plus, but it's going to become a minus because we're going to multiply 2 times negative 3/2. So minus 2 times 3/2 is negative 3 times, so let's see, negative 4/5x negative 3/2 minus 3 raised to the what? Let's get minus 2.5. 2, it's it's negative 3/2 minus 1, so it would be 5/2 or 2.5. Yeah, negative 2.5. Okay, right? Negative 5/2 or negative 2.5. Make sense? Yeah. Okay. A quick note. So I'm going to tell you this quick note you'll need for your homework, and then we're going to do one slightly elaborate problem, and then we're good. We're going to go home. The quick note I want to tell you, if the cost function is c of x, meaning you tell me how many units you're producing, and I tell you the cost. So this function, you might tell me you're producing 100 units, and it spits out cost. If the cost function is c of x, then the average cost is c of x divided by x. So if you're producing 100 units, you may put in 100 here, and it spits out how much that costs. And all you have to do to find the average is divide by x. Just make a note of that. It'll save you some frustration when you're working through this homework problems. I'm going to jot that down, and we will move on to the last problem for the night, which is number 49. Okay. The revenue equation in hundreds of millions of dollars for barley production in the United States is approximated by this revenue function. R of x equals 0.0608x squared plus 1.4284x plus 2.3418. So Sanjay, it's just a decimal times x squared plus a number times x plus a constant number 2. That's the revenue function. So, first question is asking us to find the marginal revenue function. What is marginal revenue? You want to do what marginal revenue from economics is? It's the cost of producing one more unit.
So if I were to go one more on the x-axis, how much would it cost? Essentially, one more on the x-axis, how much would it cost on the y-axis? So that's marginal revenue. And to find marginal revenue for given a function, all we need to do is find the derivative. Because derivative is the rate of change at any point. And marginal revenue is the rate of change at a specific point. I said, what's the marginal revenue at 1,500 units? Which means, what's the rate of change right at 1,500 units? Well, to get to 1,501 units, you're going to need to spend $6. To get from 20,000 units to 20,001 units, you're going to need to spend $4. It's going to go down because you've got economies of scale or whatever. So, derivatives give us marginal revenue. So, now that you know that, let's find the marginal revenue function for this equation. And I'll write it on the board for you, Sanjay. R x equals 0.0608 x squared plus 1.428484x plus 2.3418. Sorry, I ran out of room. But you all start working on that. So find the marginal revenue, which means you're going to find the derivative of this function. Marginal revenue function, all you're doing is find the derivative of it. Everyone got it? Good. Brandon? Okay. So, revenue function. So we input bushels, and it spits out revenue. So we say 100 million bushels, it spits out how much revenue will be produced for that many bushels. To find the marginal revenue, which means how much more revenue for 1 unit of bushels, and this is in very large units, but 1 unit is going to be the derivative. So let's find it. All right, r prime of x equals, but 2 times that, right? Which is, what is it, Nikita?
1.216.
1.
0.216.
Say again?
1.216.
No. No. 1 point. No, that's wrong. What do you got, Brandon?
0.1216.
0.1216. Right. Does that make sense? Okay. All right. Times x to the 1. All right. What's next, Nikita? Well, we've got an x here. So we have what we have to do for the 1, so the 1.428 times x. This x is like x to the 1. So how we do the power rule is we take this 1 down, multiply, so it's 1 times 1.428 times x to the 1 minus 1. So 1 times that is 1.428 times x to the 0. Alright, and I know why you're thinking it's 0, because this x equals x to the 0 is what, Nikita? 1. Okay, so we've got 1.428 times 1, which is 1.428. That makes sense, everyone? Sanjay, you with us? Okay. Plus 1.428. And, of course, what happens to this junk here? What happens to this? It just goes away. Constant rule, it's a constant, it's 0, plus 0. Okay? Does everyone like it? Should we do that again? Do that again? Let's do it again, just for fun. Alright, this is x, this is r of x. Let's do r prime of x equals 2 times this, which equals what, Nikita? 6x, x to the 1, plus, alright, this is x to the 1, so it's just 1 times that times x to the 0 is 1. Got it. Okay, we got the marginal revenue. So if I want to know the revenue at, what are the units here? Find the revenue in hundreds of millions of dollars and hundreds of millions of bushels. So if I produce 200 million bushels, how much revenue am I going to produce? Which equation am I going to use? This one or this one? The first one. I'm going to put 200 here, and it's going to spit out a revenue. All right, if I want to know how much revenue I will produce at $400 million, how do I do that? I want to know how much revenue I'm going to produce at 400 million bushels. How do I do that? First equation. Exactly. I want to know the marginal revenue at 600 million bushels. How do I find that? Second equation. Fantastic. Okay. So I think part B and C pretty much ask us that. B is find the marginal revenue for the production of 500 million bushels. So keep in mind that the scale is in hundreds of millions. This is hundreds of millions of bushels and hundreds of millions of dollars. So $500 million, 500 million bushels, it wants to know the marginal revenue at that point. So which equation do I use? Marginal revenue. So I put 500 in here. And what do we get? R prime 500 equals 0.1216 times 500 plus 1.428. Someone want to crank that out for me? $62.228. It says 2.0364. Yeah, it's not 62. Now, are you forgetting that there's the point here, Brandon? Did you get the point? There's zero. There's another 0 here, Nikita. Brandon? You both got it wrong. What's 2 times 0.0608? Put that in your calculator. We need to go back a minute. 0.0608 0.08 times 2.
1.12.
Oh, sorry about that. Sorry to confuse you.
608
What?
608.
I'm sorry, what?
I got 60 times 4.
Really?
It's still going
Let me see. Let me try my. I'm reaching my pockets here. Okay. So what do we do wrong? We put 500. We're in millions. So 500 times 10 is like 50. Find the marginal revenue. For production of 500 million bushels. Marginal revenue function. Oh, okay, my bad. So it's in hundreds of millions. The units are hundreds of millions. Okay, so what that means is, instead of 500, we put 5. So 5 are the units, and it's hundreds of millions of bushels. So we want 5 hundreds of millions of bushels. Now try it.
2.036.
It's 2.036. Sorry, that was emotional. Rough times. I even accused both of you of getting something wrong earlier in the class. I'd like to apologize for that outburst. It was like we were so close. I'm like, wow, man. Okay. And it was my fault the whole time. Sorry. Okay. The last question, the marginal revenue at 700 million bushels. All right, whenever you got it, Nikita, just give it to us. Yeah. Oh, okay. All right. So let's go back. No problem. All right. So we put 5 into this function. So instead of x, we put 5. So revenue 5 equals. I'll just redo it right here. Equals 0.1216 times 5 plus 1.428 equals what, Nikita? $2.036. Okay, makes sense. All right, all we need now is R prime of 7, the marginal revenue at 700 million bushels. Whenever you're ready. 2.2. That make sense, Sanjay?
Yeah.
All we do is we put the 7 here, and we're rocking and rolling. Okay, and you all got the updated syllabus that I sent out over email? Okay, yeah, just check your email. It just cut a lot of the homework problems so we can concentrate on some specifics rather than quantity. So just do that, and should be fairly straightforward. We'll expand this material a little bit next week, and then we'll be ready to review and take the final. Great work tonight.
Professor,
Yes.
I get another shot at quiz 4 and 5.
I think we'll work that out because everyone gets everyone gets 100% on quiz 1, 2, and 3. So that's what.
The same thing like the keys and I was doing it to the textbook formula. My answer was correct, but it appears.
Okay, fine. So yeah, this is the quiz. Some of the quiz questions I just maybe made a little bit too hard, but I wouldn't worry about that because so I'm giving you all 100% on quiz 1, 2, and 3. So try your best on quiz 4 or 5, and then there's 2 more. There's one quiz which will be due next week, which will cover this material, and last week's material, which is the same thing. We covered everything in one day, and then there'll be one other quiz. Do your best on those. But I mean, I wouldn't worry about it. I mean, I see you all as definitely B or A students. So if it looks scary based on your quiz score, I will definitely weight higher on the final. In fact, I'll say this. Whatever you get on the final, that's the lowest grade I will give you in the class. So if you get an A on the final, you're gold. And the final is just the exact same questions that are on the quizzes, just with different numbers. Just mixed up a little bit. So, yeah, does that work? Is that fair? Okay, excellent. See you next week.
Question